I will be just talking about mostly on the satellite-based observations. What is exactly and how it takes observations? Because this is for the mostly for the teachers, school teachers, as well as the students of the maybe the 12th class or similar type of students will be there. So I was thinking I will just brief about that, what type of how it takes the data, how you get the data, what type, how we do it, that analysis, and what you get formally. People see that this is the remote sensing or satellite, what satellite does exactly, and what type of different prospects are there in this, and how you get the data, or you can go through these other resources for getting the data or knowing the what type of applications we are carrying out. So full thing may not be there because that time 40-45 minutes I will try to cover. And anyhow, we can have discussions also as later on also. After this also, anytime people can contact with me or my colleagues. So thank you very much. My slides. Yeah. So I will just told that I will be talking about the remote sensing, because this is whatever satellite observations and everything what we call it. Basically, it is through the remote sensing what we call it. And in very simple term, what we call remote sensing is what we hear or see without touching. So that is the mainly what we call it to be remote sensing. Anything what we, even I am suppose seeing you and when we do face to face each other, that is also actually in actual term, that is also remote sensing. Or we are, when we hear without anything, like when we say the Bluetooth, that is without that is in the actual term, if you say that is remote sensing. That means or if you want to get any information in our term, when we go for the satellite remote sensing or the airborne remote sensing, in that normally we call it, that means seeing the earth surface. And nowadays, yesterday also you heard from Dr. Prakash about that, what we're talking about, that other planets. So those also we are doing remote sensing. But I will be talking mostly about that remote sensing means how you see the earth surface from the space. So for that purpose, mainly all the science students must have read about this electromagnetic energy, electromagnetic radiation, which is mostly the light waves or radio waves, what we call it. So major thing is in that through electromagnetic radiation, we get this all this information what we getting in the from the to the satellite, from the Earth, as well as from the in between also, not only the Earth, from the atmosphere also. That also I will be touching briefly because we don't have time that much. So about the atmosphere also, you might maybe hearing or in last week also we had a severe cyclones, 2 cyclones were there. So about that atmosphere also, atmosphere conditions also, you get that data from these satellites. And there are various applications. So you can go to any field. There are a number of applications in the geology, oceanography, cartography, agriculture. You may be hearing pollution. There are whatever name you take, there are applications in the remote sensing. And there are platform, if you say how you take this information. Mainly one is the ground base also is there, as I was telling. We have some radars, what we call it, Doppler radar and other type of radars, as well as other instruments also, weather stations. All those also take the measurements of these things. So these take the information regularly based on our requirement, and then we get the data transmitted to the ground stations or the where we want to process the data. Then second comes the airborne. That means from earlier it used to be the aircraft based. Lot of aircraft especially made for this purpose, where we have the instrumentations on the aircraft. Through that we take the data, And nowadays, you may be hearing that UAV-based, drone-based also instruments have started coming. But these are only small instruments. You cannot take very, very big instruments on those, because end duration also less. Can not go for the large scale, as well as you can't go for the long time. But these are very, very useful type of instruments for the local data collection. And then anyhow, one is the satellite-based. Major advantage of satellite-based is that because you get the data regularly for the many years, because satellites are normally being built 5 years, 7 years, and they work. So some are working more than 10 years also. So through satellite-based also, we get the data continuously, as well as for the all over the globe. That is also one of the major advantages. I say I will coming upon all those things, how we get this data for the all the globe, and then a long time. So if you see the electromagnetic radiation I was talking about, basically this is what we do in remote sensing in the electromagnetic spectrum. This overall electromagnetic spectrum we see, there are 3 regions mostly when we go for the Earth remote sensing, Earth-based remote sensing. We work in the visible light, that is what we see. Optical always we see from the eyes, 0.4 to 0.7 micron. Then it comes the near infrared, and then long wave infrared, short wave infrared, that is IR we have to call it, and thermal infrared. So this region is also there, which we can't see directly from our naked eyes, but in the mostly in the because of the emission, you get this all this data or information from the Earth surface, as well as for the in between atmosphere. So second is the thermal infrared, and another one is the microwave, which is give the day night also, because this is the wavelength of the maybe the centimeters scale. So in the case of the even when the atmosphere is not very clear, like clouds are there and a little bit rain is there, and even night. So that time also you get the information, because that time you cannot get from the visible information, optical sensors. So microwave. So basically these are the majors in the regions in the electromagnetic spectrum, through which under which we get the all these sensors are being developed, and we get the information using different type of sensors within this range. Yeah, as I was telling, so these are the optical systems are there within the wavelength of the visible, as well as thermal infrared. Both are we call it optical. Then another one is the radar systems, which is works in the microwave regions. I will telling about all those things later on. For the optical systems, main source is the sun for the visible, because you are getting the energy from the sun, and it is what is reflected back from the atmosphere, as well as from the Earth surface, that you observe in the satellite, as well as other platform in the aircraft also. That is through reflection. And then in thermal infrared, whatever emission you are getting from the Earth surface as well as the atmosphere, through that you get the in the IR region, or I will calling infrared as IR region in that. And then microwave, mostly for the you are getting scattering from the or the emission in the microwave. Also there are 2 are there. One is passive microwave, one is active microwave. Passive microwave means I'll cover passive sensors which are actually not having their own what is radars or instrument from where we get the energy. So those are the passive sensors, and the active sensors, they have their own radars and system which give the energy, which transmit the energy, and you get back. So these are the basically regions where we are working. Yeah. So in passive, mostly we are getting a naturally produced radiation, that means from the sun, whatever energy is coming, and then it is reflected back. That's why daytime we can see all those phenomena and information, as well as from the Earth itself, whatever the emission is there. To those also, the range we get energy, and that those are the passive sensors. That means they are not having their own a system for the transmitting energy. They are not transmitting anything. Only receivers are there, what we call it. So these are systems are called radiometers mostly. Like a camera, what we call it, our camera is also when we take any picture. So this is the camera takes the, it is passive sensor. Whatever energy is coming from the any object, you are taking that picture. So those are the passive sensors. And active sensors, they have their own radiation or the energy to send the to the target and get the reflection as well as the back scatter. What we call is scattering. That means you are sending something and getting scattered back that energy. So those are called the active sensors. Only in the microwave quality, these are the three type of sensors are there. One is called the radar altimeter. As the name itself says, altimeter means to get the distance from for any target. So it is mainly used from the purpose of the sea level. You might heard the climate change point of view, how you get the sea levels. So altimeter type of sensors are mainly for that, mainly for the sea level, and many other applications are also there from the ocean as well as for the land as well as the ice also. So these are there. Then another sensor is a scatterometer, which is the sensor also active sensor, but not looking at the nadir. Nadir means it's not looking at the 0 degree, because for any getting any distance, you need like to see the exact down. That means the 0 degree or nadir. Scatterometer is the sensor which looks at the another angle, maybe a 30-40 degree. Depending upon that what type of information. Generally, we take 30 to 60 degree angle it sees, and from that it get the back scatter. That means scattering all this energy, whatever you send the energy, like suppose you send the energy x, then 0.5x or 0.4x, depending upon the what type of targets are there or what type of information is there, how target is oriented toward your sensor. So all those things it takes in common. So by that it gives the takes back the energy, and then you get that information. This is a sensor mainly used for the ocean surface wind. That is from the surface. Through that, actually, this is very important information for the point of view. We say the numerical weather prediction. Whether you get all this information about the weather, and then how you predict it for the long 3 days, 5 days. For that, you need this information to assimilate in the model. So those are actually more details. I will not go about that. So this is another type of sensor. And third sensor is synthetic aperture radar. This is the sensor similar to the scatterometer, I can say, but it is very, very high resolution. Resolution I will come upon. That means very, very fine information you can get. That basically, SAR, you can say the very, very fine information, detailed information in respect to all other sensors you are getting in the microwave region. So this synthetic aperture radar, as name says. And another optical is also one sensor is there, active sensor called LiDAR, similar to the synthetic aperture radar, that is optical. So these are some of the sensor, passive as well as active sensors, what we call it. Yes, when I was talking about that, how do you get the information? That means you are having the radiation either from the sun, that is you are getting, or from the active sensor, you are sending some information through radars. That radiation will be having interaction with the medium itself. Medium I means to say atmosphere. Whatever in, but because your satellite is almost some are the 800 kilometer of 1,000 kilometers, some are 36,000 kilometers, like geostationary. So when there's signal is coming, and signal has to interact with the medium, because there is some medium. There are different type of gases are there in the atmosphere. So there will be absorption will be there, emission will be there, what we call it attenuation will be there. So that interaction will be there, which will depend upon the what frequency or wavelength we are talking about, because these sensors work, as I was told previously itself, from the optical 0.4 to 0.7 micron to the 100 centimeter in the microwave. So depending on the what type of frequency is there, your because the size of your particles are different atmosphere constituents are there. So it will have a interaction. Depends upon that. Many other things like a polarization, angle. There are many other things are also there. Based on that, you have the interaction from the matter, what we call it, as well as the your incident radiation. Due to that only, because of these different phenomena, you get the information about the or different constituents, and you get the classify different things on the surface of the earth as well as the atmosphere. So as this cartoon shows, in the energy is there in the terms of the sun, and it is coming to the earth surface, and then at particular angle it is going, as you know, you might have read about Snell's law, all those things also. If its surface is very smooth, that means flat surface, it will have angle of incidence, angular reflection will be same. But if their surface is not smooth, rough, then angle will be different, it will be going some other place. So by that, basically through this phenomena, you are having the energy getting into the systems or your satellite system. And in that, in between, there is a transmission I was talking about, because you are getting energy from a system, so the transmission will be there. Then some absorption will be there from the atmosphere itself. Will be some absorption will be there based on the constituents, based on the gas, as well as the absorption when it's reaching to the surface of the earth, like land as well as the ocean. Even then also there is some absorption of the energy what we are getting will be there. And in addition to the absorption, there will be emission also, because at different wavelengths, energy will be emitted differently. So emission is there, one of the phenomena. Then scattering, as I was talking, all the energy what you are getting in the sensor, that will be scattered back. Part of that energy will be scattered back also. And reflection. So all those phenomena takes into account when we are talking about that information content, what we derive from the satellite data or using the sensors based on the any particular satellite or any particular information. So basics of telling these things is you can understand now. When we say I am able to identify particular type of crop by seeing the eye directly, if I go to near to the any field, I can identify based on my experience, because that also goes on experience. I can say this is the wheat, this is the rice, a particular type of rice, particular growth is there. But if you are seeing from the 800 kilometers away, and in between, so many phenomena are also taken into account. So how difficult it will be there to get this classification as well as the information content generation based on all those phenomena, all those physics, as well as the vertical related transfer equations we solve, and other training things, and as well as the other data what we collect, because when we want to classify anything, we need the other data also. Not only this information itself is not sufficient. So based on all those things, we get this information. So anyhow, we discussed this thing. One is we get the information. Earlier we used to get the aerial photography, that is also remote sensing, and but this is cannot go to the very large scale. Only the at particular time you having a few kilometers only, and anyhow, the 3 to 4 hour flight if you go, you will get some data, and then processing of data, storage of data. All those many issues are there in the when you go to the aerial remote sensing. But advantage is there, you can fly very near to the surface of 6 kilometer, 8 kilometer also, based on the what type of sensor, what type of information you want, and anytime you can go to the place for the testing of instrument. Mainly for the if any instrument or any sensor when we developed, we go accordingly what type of information we should be there, what type of sensor should be there. So accordingly we make that test those sensors. And anyhow, satellite remote sensing, what we are talking based on the different type of satellites. Yeah, then satellites, there are two types of basically what we will be talking about, the two types of orbits. One is geostationary orbits. Geostationary means it is seeing same place all the time. That means the orbit is around 36,000 kilometer orbit is there. We are not going much detail into that, but it can be solved by the equations. We can see around when it is around that height, then with the spin of the Earth as well as the spin of the satellite, both are exactly same orbit. So because of that, you are seeing almost the same area all the time. And this type of orbits are basically used for the weather satellite. That means for seeing the atmosphere phenomena. So, and another type of orbits are the polar orbiting or synchronous satellites. They are orbiting all over the world from the mostly, I can say, pole to pole, approximately pole to pole. And the orbit is around 100 meters. In around 100 minutes, it covers that one orbit, and then it by the time your Earth is also moving, so you will cover another area. Like that, it go on covering the whole Earth in approximately depends upon the sometime is 2 days, 5 days, 10 days. What type of orbits are there? What type of precision is there, and many other things, and what type of your requirement. Based on that, we have a different orbits in the polar orbits. There are many other orbits are there, what you call the geosynchronous orbits are there, Molniya orbit are there, very, very highly elliptical orbit, which are basically for this purpose of the seeing the high latitude regions. So, but mostly we use a geostationary and polar orbit satellite for that. This is one of the picture taken from web only. This is aerial photography. Very clearly, you can see the very, very fine information from the any aerial photograph. And this is one picture from the satellite image of our own satellite, high resolution. This is Hyderabad only. You can say Sensagar Lake and Airport. So based on the resolution and all those spectral range, we get a different type of information. In the sensor point of view, what we call it, I will coming about the resolution also, but overall area what sensor sees is what we call the field of view, FOV what we call it, at a particular time, total area, how much is seen the field of view. And in each sensor also, there may be many detectors, so like 30, 40 detectors are there. Each detector will be seeing one particular area. That is called a instantaneous field of view, or we call it IOV. So that is the basics of how you get that information about very, very fine information based on the what type of detectors you are having. And each sensors, as we can have suppose 4 sensor, 10 sensor, or 20 sensor. Each sensor will be go on taking information at particular point of the Earth. The sensors are adjusted like that for the same point on the Earth. You get the information from the different channels or the spectral bands. Like in this case, we are showing from the red band, green band, blue band, and infrared bands. And then all this information for all these pixels, what pixel means each point, what we call it, and the scan line, that's why you get the whole image. So based on that, you get the total area and the information about that. I will be coming later on in detail. For each pixel, how you get the different type of information. That is basically because of this. For suppose like this sensor, for first point, you are seeing the red band in 0, second is 2, green band 10 and 12, blue band 20. So if I process accordingly, if I see in the blue band only, then I will get particular information. If I combine blue and green, then I get different form. So this way, we select the sensor accordingly also what type of information we want to generate, and when we want to classify or derive the information, that type we use choose those bands. So, and remote sensing, one thing is basically comes with the resolution. The resolution are the basically of the 4 types. One is spatial resolution, that means the area wise what we are seeing, the smallest area what we can see or detect from any particular sensors. Some of you might have heard of also what we call the 0.2 meter resolution, 0.5 meter resolution, 1 meter resolution, 10 kilometer resolution. So those are the means. A 10 kilometer resolution means you cannot resolve the information less than 10 kilometer by 10 kilometer. That is approximately, if you see 10 kilometer, 10 kilometers are approximately 100 square kilometer. Similarly, for 1 meter resolution, you can take an area 1 meter by 1 meter. Basically, exactly it is not 1 meter, 1 meter, because if you plot the overall histogram, there will be some 3 dB bandwidth will be there. So, but approximately this is 1 meter means less than 1 meter information you cannot derive with very high accuracy. So that is a resolution, what we call it, a spatial resolution. Then comes the spectral resolution. That means how many spectral bands you are having. I was earlier slide, I was talking about that red, green, infrared. So what type of spectral, like 0.4 nanometer to 0.4 to 0.45 or 0.4 to 0.41 only I am having. So based on that, what type of spectral information I want, or what type of sensors I can make. So those are the spectral resolution. That means one line in the spectroscopy you might have learned that line widths we call it. So for any channel, particular spectral line will be there, and around that you can make the channel broadband or the very narrow channels. So that's called the spectral resolution. Then third is the radiometric resolution. That means how many digit or bits you want to get the information. You get 2 bit, 4 bit, 8 bit, 10 bit. So that is called the radiometric resolution. That is also depend upon how much information you want and how much information you can store in the satellite, because satellite or sensor also are limited by the total systems storage also. It cannot go on storing because it has to download at some place. That's called it the ground stations, different ground stations on the globe. All the country have their own, and with cooperation they use the others also. So based on all this information, when you are seeing from satellite any ground station, then only you can download that data, whatever has been gathered. So based on all those things, radiometric resolution is also defined accordingly. And then fourth one is the actually temporal resolution. Temporal resolution means after how much time that particular information or particular area is being covered. As I told, some like geostationary satellite is seeing every 5 minutes, 10 minutes, or half an hour, 1 hour, the same area, because it is at same place. So it can see at very, very fine temporal resolution. But orbital, like polar orbit satellites, they come sometime in 2 days, 4 days, 8 days, like that. Like IRS type for 23 days, maybe 25 days, some are there. So this is called the temporal resolution. So our information generation, we need to keep in mind all those resolution also, because the sensor will be developed accordingly, and because the complexity also increase when we in the sensor wise as well as your satellite wise, all those things. This is one example of resolution. If you just can see left hand side is 0.5 by 0.5 meter, and this is 2 meter. So 0.5 meter to the 10 meter, if you see all these images, then you can understand 0.5 meter you can see very, very fine resolution information. But in 10 meter, all this information, same information, we are just averaging to showcase. It is not from the different satellite has been taken, but suppose you take 0.5 meter versus the 10 meter. 10 meter you can see those information very clearly. So that is advantage of resolution. But is the disadvantage when you go to very, very high resolution of this type. You need a very high storage as well as data download, and sensor also should be of that quality. And then so that's why based on the, I know you don't require for the very, very high resolution for each and everything. For cartography type of purpose, we require very, very high resolution. Otherwise, we can go for the 5 meter, 10 meter, depending on the what. And these are the different resolution as well as the different spectral also. Like first case, we are talking 0.6 meter resolution, which is our own cartosat, what we call it. Then 1 meter, and this is and the right hand side cartosat 2, 1.6 meter. So there are different channels are there. They are having different resolution, like what is 0.5 meter is their pan, as well as 2 meters, suppose it is there your spectral channel. You can combine those things also. That means both the information, you can take advantage of both the information, high resolution but in one channel only, or one color, what we call it black and white. But different colors information, but it's not very high spectral resolution. So by combining those things, also we get the various type of information. So this is one examples of that how we get the different channel information, and from that, starting from that, we have the up to the 56 meter, 72, 56 meters AWIPS data, what is called advanced wide field sensor, then 72 meter, like that, different type of information for the large scale information, which is not changing very frequently, and especially also for that we don't need very high resolution, but we get the larger swath means ki total area, how much we can cover. So based on that, these are different resolutions are there. Spectral resolution, as I was talking about, yeah, basically if you see spectral resolution, what we call it is the black and white image, black and then the blue, green, red, basically three colors, everything, all colors are made. So 0.4 to 0.7, if you have the only one color, so that is a black and white image you get. But based on three colors, all these things, you can see the peaks of different colors will be different based on the what type of your target is there. Then you get the information, three band. Then multispectral band means ki each channel will have a particular width. So these are the multispectral channels, sensors are there, and then comes the hyperspectral sensor. Hyperspectral, very high resolution, spectral resolution sensors. Bottom you can see that information is there. That is one image or particular area is there on this side, front side. But on the other side, one is different spectral bands are there. So these colors you may be seeing yellow, red, and violet. So these are different spectral channels or particular pixel only. Pixel means particular point in the earth, what we are seeing from the different bands, spectral bands. So using those things, we get the different information and different, here we are showing only the colors, so that means the false color composite. But really, if you for the analysis or classification, we use the actual data, because you cannot visualize those things clearly. But this is 3D cube has been shown, but you cannot visualize clearly. So for visualization, you use only the three bands, any three bands, and based on that you get the all these information. So hyperspectral are also being used, but these are very complex type of systems are there, as I told, sensor wise itself, and the data collection and downloading, everything is involved, huge amount. So based on the information, what type of information we want, we get. Yeah, this is one example of how you see any particular area in different channels. In blue colors, if you see, ocean is seeing dark, vegetation is dark, cloud is seeing bright, and non-vegetation, that is parent line type of this is seeing bright, snow. So different combinations of the target you are seeing in the one particular band. If you go to another band, that green band, then you see in different way. So those targets are seeing in different band. Then in red band, you will see same target in the different way. So that is the purpose of showing only that if you combine these three, this is only example of three bands. So one particular image or a phenomena itself, if you see from the different bands or different channels, you can classify those things. That is the purpose. Then anyhow, radiometric resolution I talked about. This is the how you discriminate between the different bits bitwise, that is 2-bit or the 8-bit or 16-bit data, 12-bit data. Bit anyhow, you all of you, because nowadays computer is everybody is learning. So how we define the bits, 2-bit data or the 8-bit data, and basically it is that as you see, 2-bit you can have the information up to the 4. But if you have the 8-bit data, then information 0 to 255, that is 256, you can have the resolution up to 1, 2, 3, like that. Any information can be up to the can be 1, 2, 3. But if you have 2-bit data, then information can be only 0, 1, 2, 3 only. So whole information, when you are dividing it only in 2 bits, then the information itself is many information is lost. So as many more bits you have, that means more radiometric resolution, you can store the information, much more information from the same sensor. Even sensor is same, but information can be, when you are storing, it depends upon the what arithmetic resolution is there. Like this, one is a 2-bit versus 8-bit image. Clearly, you see the difference between these two. How your all of the resolution are same. Even then, information is degraded. Then temporal resolution, anyhow, I talk about that is a different satellites, how the orbit takes place, and then based on that, you get that 5 day, 10 day, 20 days, like that. Okay. So now this also many of you might have read, because this is one of the basic when we go for the remote sensing things. All these laws, like Planck's law, which is basically what deals with the black body. So how, depending upon that, this is just you don't go much detail. This is the overall brightness, what we call it, or the spectral brightness at particular. Nu is the frequency or the wavelength. H is the Planck constant. Nu is, this is the, as we can see, and all the T is the. Here is the mostly you see the what is the thing where variables are there is the brightness, temperature, or V, or spectral brightness, frequency, as well as the temperature. Actual temperature, physical temperature. All other things are constant. C is constant, H is constant. So we play with this based on the frequency at which you are working in passive, even in the active. Passive, you have receivers, because you don't have any active sensor but receivers. So receiver at which frequency is there, you are observing, as well as the temperature of the surface, that means Earth surface or the atmosphere, what you want to take information. That accordingly you get the brightness or the energy. So this is a overall equation. That is Planck's law follows all these remote sensing instruments, and depending upon the what frequency you are working, like very well the low frequency when you are working, this is law is simplified, and then directly it is related to the temperature. With the brightness, temperature will directly relate to the temperature, like in a microwave. Then for the very high frequency, this law itself you can approximate in different ways. So this is just an example for that. Similarly, for the different law, what we make it based on the Planck's law only. That means at which is the maximum radiation occurs at for particular temperature. I will come upon that. So to tell you that how you get the different energy from the different type of matter in the land. So brightness, temperature is, I'll just briefly say, because nothing is a black body. Black body is actually perfect body where everything is absorbed 100%, or what we say, same thing is emitted 100% emission or 100%. But nothing is a black body. So it will depend upon the emissivity, but how much emissivity of particular this epsilon is there of particular target or particular type of matter is there, and basic temperature, that the actual temperature of that, if you multiply that, then you get the brightness temperature what we observe in the satellite, in the passive sensor. This is the brightness temperature we get, not the exact temperature of because in emission what you are having the sensing is the radiation only, that is emitted radiation. So emitted radiation directly you get in the form of the brightness temperature, which is dependent upon the directly on the temperature of the actual what is surface. Yeah, so I was talking about this. You see, for the different type of actual temperature, this is 100K, 6000K to 10 billion K. How at different frequency, what is the maximum radiation will be there? So, like you see around 100K or 300K, what is the Earth temperature, that is in Kelvin. That's why you get 300K. So at this frequency, around that 10 micron, get the maximum. So if you have the sensor around this frequency, then you get the maximum radiation, that means maximum energy. Otherwise, if you have the sensor in other regions also, but energy will be less. So total energy will be less. Your detection will be somewhat less. Similarly, for the sun, 6000K. So your total energy, as you know, what we see in the visible range only, and that is 0.4 to 0.7 micron. But whereas in the Earth 255K range, when we call it, that is around 10 microns. So that's why for the all these sensor in infrared is when the Earth's atmosphere we are seeing, in the emitted radiation is in the range of the around 10 microns. So that is the purpose of showing that based on that laws, Planck law and then wind displacement law, how we use these things, science in this. And this is the overall, you get the brightest temperature, how you get. This is the sensor at the TB, what you call it, at the sensor you are getting, but it is dependent upon all those things. From the this example of ocean, you can take ocean or land, anything. So whatever information is coming from the sun to the land, and then brightness temperature, it is some emission is there, that is ES, what we call it. It will downwelling, that means something coming down, then it is going in the atmosphere itself, and combination of all those things. TS is the surface temperature, and this is the ES is the temperature in the emission from the surface. Then upwelling is the how much atmosphere is taking. So all those things information together, combination of all this only we get in the sensor. So we don't get exactly from the, suppose I want to measure anything on the surface, I don't get directly that. It is always combination of many things. That's why we need many channels also, or many bands also, because to classify or differentiate between different things in the. And another problems, we can say the problem also and solution also, because atmosphere is there, the atmosphere also absorbs radiation in different frequency band, like oxygen is there, water vapor is there, carbon dioxide. So if you are seeing from, if you want to observe anything on the land or the ocean, but in between there will be absorption by these bands also. So you have to avoid these bands. That means your channel should not be at these bands. But even then, at even absorption will not be zero. There will be minimum absorption. So for anything what we take observe from the Earth surface, we try to avoid these absorption channels. But if you want to observe anything in atmosphere, like if you want to observe oxygen or maybe the carbon dioxide or whatever, then you use these band only, so that that whatever information you are getting on the satellite, you are mostly getting from these bands, and that impact of the Earth is very less. So based on the requirement, as I told, we devise the channels accordingly, as well as the sensors are made accordingly. This is also one example where the reflectance curve is shown for the different type of body, like for the snow, you can see clearly this is one of the different channel how the reflectance takes place. Similarly for the ocean, how the reflectance takes place, as well as for the soil and the type of vegetation in different areas. So based on these combination, we make the sensors. Also, when we make any sensor, we take into information by the theoretical calculation, what is the sensitivity of that. That means for any particular type of information I want to take, how much sensitive for that particular, like for salinity we are taking, salinity is around 1.4 gigahertz we take. If we go for the make channel at any other frequency or sensor any other frequency, then information from other parameters like wind, water vapor, as well as the other atmosphere contents will be also included. So sensitivity of this whatever parameter I want to define will be less. So based on these calculation sensitivity studies, also we make the define the our sensors accordingly. Overall, when we get the data, this is the flow, I can say. You are getting data from the satellite or the aircraft. You get the sensor data. That means whatever sensor is observing, you can say reflectance, brightness, temperature, scattering coefficient, and some auxiliary data from the satellite, because orbits are there, what type of orbit is there, where it is, that many other information is there. Auxiliary data also goes into that. And then it go to pre-processing. That means all this data, because you are getting in voltage, actual data you get in voltage count. Then you have to convert into information what exactly we want. So a lot of pre-processing is involved in that. Based on the pre-processing, we made the data products in our systems. And from these data products, we use the field observation also, as I told in beginning itself, because the data will be some numbers will be there, data for some numbers will be there. How to get the information about particular type of information for the useful by the application scientist or for users. Then number of retrieval technique, what we call from these observation, how to get the actual information, that techniques we develop. Based on these techniques, we get the actual geophysical parameters, which is the parameters like I can say in the ocean, how much wind is there, how much water vapor is there in the atmosphere, or how much vegetation is there. All those parameters we define based on these things, and then we analyze this data for the different time frame, different regions, locations, and then we make it value-added product. That means some other products which are easily usable by the any public or the users or scientists, and based on those we have a number of applications. So this is the overall workflow, what we call it. There are many things involved in each stage. So similar thing in the data processing pipeline. In processing itself, if you see what I was saying, pre-processing, you have the data acquisition, that the ground station is involved, where the satellite puts the data. Then this raw data and auxiliary information is going in the pre-processing, where the signal processing is involved, radiometric, different type of corrections are involved, like radiometric correction is there, geometric correction, that means at which location exactly is there, precise location, and then we define the actual information. So all those things in processing itself goes, and after that we get the radiometrically and geometrically corrected product. That is also for the particular areas which are actually flat, because if you are area like Himalaya and all those things, then you have to ortho rectification, what we call it also, because of the digital elevation model, those corrections also have to be made. So all those corrections to be made, and then we get the actual information, what we normally see in the public many pictures. So it's just to tell that how much important and how much interesting this field is there. So if somebody really want to work in this area, then whatever image we get, you see, I may have seen the website or the newspapers and print media. We classify these images into different techniques are there. Basically, in the optical, we can say two type of classification: supervised as well as unsupervised classification. In supervised classification, we define the representative or training samples. That means based on the field data, lot of field data collection, and what type of surfaces are there. The different processing many processing techniques are there. So that, and unsupervised also, where we don't give any training data, but we define only number of classes, and based on the training we do. So this is one example of this. You can see this is an image, and this is a classification, object-based classification, and different type of crops are there, different type of fields are there, orchards are there, or even in this case paddy is there mainly. So paddy, which stage is there, you can see by this classification technique what were developed. You can identify with a certain accuracy. Here also I will again say, when we do this, not 100% accurate is there because of the many reasons I told. There are many features involved, processing also, sensor involved, as well as classification techniques. And because you are seeing a particular area, what we assume with pixel, maybe suppose at 10 meters, it is not exactly at that 10 meters. Maybe nearby pixel information also is coming into this. So all those things are there. This is also one example of the 3 bands for the same thing. You can see the near infrared, red and green. Same information if you see from this 3 bands, you see how it looks. But here I have taken the different band. Earlier you see this was a infrared, red and green. But now this information has been red near infrared as well as red edge band. One is called red edge band also has been taken. Then information, totally different information you can get. When you get a near infrared, red and green, then information content different. So when we are having many channels, see, you have to define what type of information is there you want to derive based on your experience, simulations, as well as field data. All these informations are being classified based on this. So that is basically classification wise. And just last, I will talk about what type of sensors presently are there. This is one resource set, I call it a different resolution, talking about multispectral as a pan, starting from 6 meter to 56 meters. Then for very, very high resolution sensors for cartography purpose mainly, and for the digital elevation model, goes up to the 6 meter, up to the 0.5 meter resolution. Then we have satellites for the atmosphere as well as ocean. That is INSAT. I was talking about geostationary satellite, which gives the information about that atmosphere, regular information. There are another sensor is the megatropics. Then for ocean, there are sensors. The ocean color sensor for basically you might have heard about use for the fisheries forecast. And then altimeter for the sea level, spectrometer for the wind vector. These are number of sensors. In addition, we also use the right hand side. You see the number of ground stations or ground instruments, automatic weather station, rain radar, and buoys in the ocean, that is calibration, validation, as well as for the information content generation. So with the combination of these things, we are using. This one example, overall example, because other example land I have shown. This example for the cyclone, because cyclone was in the last 2 weeks back. So how we get the information, how we do disseminate the information. Cyclogenesis, people left hand side. That means when cyclone is being generated, means being developed, that time itself using the satellite data, that is spectrometer data, we try to get the information that is this will be developed in the cyclone. Particular feature from the atmosphere will be developed in cyclone or not. That we give cyclogenesis 3 to 4 days before the cyclone. Then after cyclone is developed, then we give the track where it will be going based on the numerical model as well as the empirical models. We give that. And when this track is given, that means how much area it will be covering approximately. Then we also try to provide that on the ocean side, how much area can be maybe told to the shipping corporation and other people. Then we regularly monitor these things, cyclone, where it will be hitting and give the prediction. And in the ocean also, where it will be, how much sea level will be there, that means surge will be there, how much wave height will be there in the ocean side. And after that, how much inundation is there. That means how much area has been damaged when it reaches to the coastal area. So right, left, bottom you see that is cyan color, that much area, recent cyclone is the Yas cyclone. How much area is inundated based on the different images or the satellite data from the microwave mostly we use, because that time cloudiness will be there. So how much area inundated is useful for the planning purpose. That means this much area has been inundated based on the digital elevation model as well as the satellite data. We get this. And right hand side you see this is the pre-cyclone versus post-cyclone, 2 images clearly. It shows that how much area has been inundated, submerged area, flood inundated. That so those information also we give to our websites, and these are the websites. Normally we provide information. You can go to any website of these for getting more detail about this, because this will take a lot of time if you want to discuss. One is the Bhuvan website, where we get the many information as well as the satellite data also. Most of the satellite data you get from this website, as well as some applications what we are doing for the different ministries as well as for different other people in the country. You get in that. Then another information center is the MOSDEC, the Meteorological Ocean Satellite Data Archival Center, where you get the mostly atmosphere ocean related parameters as well as applications, and you can see the images what we are. You see in the TV also that regular image of the weather. So this is mainly our satellite, and then techniques have been developed in ISRO, and then it has been transferred to the Ministry of Earth Science, IMD, and then they are operational agency, they regularly provide it. But we go on improvising all those techniques as well as the prediction techniques. Then bottom you see the one side is VEDAS, the visualization of the Earth observation data archival. There also you get a lot of information about these things. Different related to energy, crop, and many other things. So combination of all these satellites, and then anyhow ISRO website is there, where through that you can get the information about all our ISRO centers as well as all these websites also, where this data as well information is available. So this is all I wanted to say, and this is just in last. I'd like to thank all actually for this whatever presentation I have made. This is a combination of from the many earlier lecture presentation and some of the websites, some images and the data have been taken. So I acknowledge all of them, and thanks a lot to all of you for listening to me. Thank you.